Types of learning and then factors that affect.
Good morning, everyone. So we're welcome to our lecture 2, CHM 121 Inorganic Chemistry section. The last class we had, we looked at the periodic table and also the trends in the physical properties across the representative elements. These are the elements of block, S block and the P block. We looked at the atomic radius, it decreases down the period, it decreases across the period, increases down the group. The ionization energy of the elements increases across the period. Electronegativity increases, electron affinity, increases across the period. The electronegativity increases across the period. The metallic character decreases across the period. The melting point and the boiling point does not have a general trend. We see that the metals possess high melting and boiling points, while the non-metals possess the low boiling points and the low melting points. Now, most of the elements, almost apart from, I think, 10 elements, are metals. So all the elements, apart from 10 elements to the right corner of the periodic table, are metals. So today we want to look at the trends in the chemical properties. And the trends in chemical properties, or the chemical properties of these elements, depend on the physical property. So it's actually an offshoot of the physical properties that have been observed for these elements. As I mentioned in the last slide, as we go across the period, there is a reduction in atomic radius, an increase in ionization energy. So the tendency of these elements to form a positive charge or to give us a positive charge decreases across the period. And by so doing, once you note that the first element, the element to the left, has a lower ionization energy compared to the element to the right. So as you go across the period, the tendency to form the cation decreases, while the tendency to form an anion increases. So the metallic character of the element is affected. Now down the group, there is an increase in metallic character because one, ionization energy decreases, the tendency to form the positive ion is increased, and so the metals, or the metallic character of the element increases. Also, there's an increase in the ionic character of the compounds, and also an increase in the basic nature of the oxides. So these are some of the chemical trends or the factors that affect the chemical trends across the period. Since the ionization energy decreases as we go across the period, tendency to form ionic charge for the S block elements, or tendency to form covalent, cation, negative charge for the non-metallic element increases. And so there's an increase in the character of the ionic character of the compound. There's an increase in the metallic nature of the element of the compounds that are formed. And also when they form the oxides tend to be more basic as we go down the group. Now, as we go across the period, there's an increase in the nuclear charge. And so as a result of that, the tendency of the elements to attract, or the atoms to attract electrons, increases because the nuclear charge is increased. Also, the elements become harder to ionize. That is, ionization energy increases. So the tendency to lose the electrons also increases. So the elements, the tendency to lose the electrons increase as we go across the period. And these changes, that is the increase in attractiveness of the electrons, or attractive force for the electrons, and the higher ionization energy, results in a change in the nature of the compounds that are formed. These changes affect the nature of the hydrides, the oxides, and the chlorides, which we look at in this lecture. And to look at the trend in the periodicity of the period 3 elements, we are going to look at period 3. Period 3 starts with the filling of the 3s orbital, and it ends with the filling of the 3p orbitals. And these elements in period 3, we have sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Argon is an inert gas, that's the 3p6 element. And so the tendency for the inert gas has a reluctance to react. So most of the time we are going to concentrate on the trend between sodium and chlorine. Why are we using the period 3 elements? We are looking at the period 3 elements because these elements are more representative of the other elements. For instance, in period in period 3, we have the occurrence of a 3d orbital. The first period is period 1. In the period 1, we have only the s orbital, that is the 1s orbital. So we have 2 elements in that period. In period 2, we have 8 elements in the period. We have the 2s and we have the 2p. In period 3, we also have 8 elements in that period. We have the 3s and we have the 3p. But there's a difference between period 3 and period 2. And that difference is that the third energy level, in addition to the s and the p orbitals, also has a d orbital. Now that d orbital is not filled within the third period. It is empty. And because it is present, at all, because it is present, there's a tendency of the element, that orbital, or the 3d orbital, to be involved in bonding. For instance, you can have the elements in period 3 undergoing hybridization that will involve the d orbital. Also, we can have the elements in period 3 transferring electrons temporarily to the 3d orbital, maybe during the course of a reaction. So the elements in period 3 have the ability to expand their octet. They do not strictly obey the octet rule. The octet rule can be expanded because the 3d orbital is available. It is empty, but it is available. And the energy of the 3d orbital is not too far-fetched from the energy of the 3s or the 3p orbital. And if we look at it after period 3, the next period, period 4, in period 4, we also have a 4d orbital. Even though so we have the 4d orbital for period 4, we have the 4s, we have the 4p, we have the 4d orbital, we even have the 4f orbital. But like the elements in period 3, the four elements in period 4 can also expand their octet. So that tendency to expand the octet is present in period 3 and other subsequent periods. Is present in period 4, present in period 5, present in period 6, and present in period 7. So all the elements in period 3 are more representative of the lower elements in the periodic table than the element in period 2. Because in period 2, these elements cannot expand their octet. And the ability to expand the octet affects the chemistry of the element. So that is why we are using the period 3 elements as a representative of the elements in the across a period in the periodic table. Please remember that I mentioned last class that the elements in period 3, or the elements in the periodic table, the S block and the P block elements are called the representative elements, because the chemistry of these elements are representative. One element is representative of the group of elements. So the S block and the P block, they are more related down the group, while the D block and the F block are more related across the period. So we are looking at the trends in chemical properties of the period 3 elements. Now, if you look at these elements, sodium, magnesium, aluminum, silicon, and even phosphorus can be present as sodium, aluminum, and magnesium are metals. Silicon is a semi-metal or a metalloid, while phosphorus, sulfur, and chlorine are non-metals. Argon, I mentioned, is a noble gas. So the chemistry of argon is a bit different from the chemistry of the other members. So we want to look at the reactivity of these elements with water. How do they behave when they are in the presence of water, when water is added to it? Now, sodium forms a strong alkali in cold water. Sodium reacts with cold water to form sodium hydroxide, which is strongly basic. And the reaction is an exothermic reaction. Magnesium reacts with both cold water and steam. The reaction with cold water is a very mild reaction. It's a slow reaction, but it reacts with cold water to give us magnesium hydroxide, which is a weak alkali. That is, it is a weak soluble base. It also has a pH of greater than 7, but it is weaker than sodium hydroxide. But the reaction with steam, when magnesium reacts with steam, the reaction is almost spontaneous, and it gives us magnesium oxide. So the magnesium oxide is an ionic oxide. It is a basic oxide, and it is only slightly soluble in water. And in this case, when this reaction takes place, magnesium, it burns with a white flame. So when you have magnesium in the presence of steam, you observe a white flame, and that is what you have, gives us magnesium oxide. All of them give you hydrogen as a gas. So that reaction involves the loss of hydrogen. Aluminium reacts only with steam. Aluminium reacts only with steam, and it gives us aluminium oxide. This reaction is a slow reaction, and aluminium oxide is an amphoteric oxide. That is, it has both acidic and basic characters. It can react both with an acid. It can also react with a base to give you the salt. But the bonding in aluminium oxide is ionic. Aluminium oxide, however, is insoluble in water. It is insoluble in water. So when you have that reaction, it gives aluminium oxide, and that oxide is insoluble in water. But it reacts with acid, and it also reacts with the base. Then silicon. Silicon, remember I mentioned, is a semi-metal. So silicon reacts with water, but that reaction, it is red hot silicon that reacts. So it does not react at ordinary temperatures, at room temperatures, but red hot silicon reacts with steam to give us silicon 4 oxide. Now, in this reaction, that is, silicon 4 oxide is covalent. It is an acidic oxide, that is, it will react with a base. It's an acidic oxide, and it undergoes hydrolysis in water. So when you have the reaction of silicon oxide, it gives us silicon oxide, just like aluminum or magnesium in steam, and this oxide hydrolyzes in water. Later, we will see that the ability of silicon to hydrolyze in water is actually as a result of the presence of the 3d orbital. Carbon, which is the element above it, reacts to give us the carbon dioxide or carbonic acid, as the case may be, but it does not hydrolyze, and that is because the d orbital is not available. Phosphorus and sulfur do not react with water. Chlorine reacts with water, and it gives us 2 acids. It gives us the hydrochloric acid, which is a strong acid, and the chlorine 1 acid, the oxochlorine 1 acid, which is a weak acid. The ability of chlorine, the reaction of chlorine with water is actually what we call a disproportionation reaction. When chlorine reacts with water, it gives us 2 acids, but this reaction is actually a disproportionation reaction. What do I mean by disproportionation? Disproportionation is the ability of an element or an atom when it undergoes reaction to go to both a higher and lower oxidation state. So when that atom reacts, the atom of the element reacts, it goes to both a higher and a lower oxidation state. If we look at chlorine here, Cl2, oxidation state of Cl2 is 0. So in chlorine molecule, oxidation state of chlorine is 0. When it reacts with water, it gives us HCl and HOCl. In HCl, the oxidation state of chlorine is -1. And in HOCl, oxidation state of chlorine is +1. So we have chlorine going to an oxidation state -1, which is lower than the oxidation state of the chlorine molecule, and also going to an oxidation state of +1, which is higher than the oxidation state of the chlorine molecule. So such a reaction is called a disproportionation reaction. Any element whose atom reacts this way undergoes disproportionation. Please note. Then argon does not react with water. So we've seen that within the 3rd period, we have 8 elements. 5 of these elements react with water, while 3 of the elements do not react with water, either as cold water or as steam. Then the reaction with oxygen. Reaction with oxygen. Sodium reacts with oxygen, and when that reaction occurs, it occurs with an orange flame or a deep yellow flame. So when sodium reacts with oxygen, the reaction gives us sodium oxide, and sodium oxide, that reaction gives us a deep orange flame. In our CHM 122 experiments, by the time we get to maybe group 6, we are looking at when you are looking at the group stage, I believe when you are looking at group 6 elements, one of the tests of that element is what we call the flame test. And what do you do in that case? You put the element, the compound you want to test, you put it on a spatula and dip it into your Bunsen burner flame. What happens is that you now see within that Bunsen burner blue flame, you see another color being observed. And that other color is the colors that is distinct or unique for the element in which you have the compound being burnt. For instance, if you have a sodium salt, when you are given a sodium salt, you can now test it by putting that sodium salt on your spatula and putting that spatula into the Bunsen burner flame, you will observe that within the Bunsen burner flame, you find out that you have an orange or dark yellow, deep yellow coloration flame being observed. That is the flame test. And when you have the orange flame or the deep yellow flame, it is characteristic of sodium. Only sodium salts will give us the orange flame. And that also occurs in magnesium, because I think those are the two elements that you really will do the flame test in a CHM 122. When you have magnesium, you put a little bit of the magnesium salt on your spatula, dip it into your Bunsen burner flame, you will observe that a white coloration, a white flame is observed. That is also distinct for magnesium. So for these elements, when you are burning them in oxygen, many of them give you, or the metals give you a flame, a different color in the flame. And that color is characteristic of the element. So with sodium, when sodium reacts with water, with oxygen, sorry, it gives us sodium oxide, and that gives us an orange flame or a deep yellow flame. And sodium oxide is ionic. It will react with water to give us sodium hydroxide again. It is basic because it reacts with acid to give us the salt and water only. It also undergoes hydrolysis in water because it reacts with water, it dissolves in water, and reacts in water. Now, I just want us to point out what we mean by hydrolysis. A substance that only dissolves in water, you will say that this substance is soluble in water. A substance that dissolves in water and reacts with water. So in the presence of water, there are two things. It dissolves and reacts. That substance is said to undergo hydrolysis. So when it hydrolyzes, you say that when it reacts with water, you say that it hydrolyzes. But when it only dissolves in water, you say that it is hydrated. So when you say a substance is hydrated, that means you have it dissolving in water, no reaction. But when it is hydrolyzed, it dissolves and it reacts. So that is the difference between the two terms. Now, when you have excess oxygen, sodium will also react in excess oxygen to give us the peroxide. So you have the formation of sodium peroxide and you have the formation of sodium oxides. The peroxide has oxygen in a state of -1, while the oxide has oxygen in a state of -2. Magnesium will also react with oxygen, and it gives us the magnesium oxide that burns with an intense white flame. Magnesium oxide is also ionic and basic, just like the sodium oxide, but it is only slightly soluble in water. Now, the slight solubility in water, you may say, is not expected because magnesium, like sodium, is an S-block element and also gives you an ionic compound, but an ionic and basic compound. But because of the high charge of magnesium, magnesium has a charge of 2+. Magnesium ion has a strong polarizing power. And that strong polarizing power introduces covalent character into your magnesium oxide. So because of the high polarizing power of the magnesium ion, the magnesium oxide compound or the magnesium oxide is not as ionic as the sodium oxide. Rather, magnesium oxide has an appreciable covalent character that is introduced into it. And so the solubility in water of the magnesium oxide is lower than the solubility in water of the sodium oxide because the magnesium oxide has a high polarizing power. It polarizes the oxygen electron cloud, and thereby the compound has an appreciable covalent character in it, and that makes it slightly soluble in water. Remember, generally, ionic compounds are soluble in water. Covalent compounds may not be soluble in water. Fully covalent compounds are not soluble in water, but they are soluble in other organic solvents. Now, in the case of aluminium, aluminium reacts with oxygen again to give us the aluminium oxide, which gives white sparkles. Aluminium oxide is amphoteric, even though the bonding is ionic. Aluminium oxide is amphoteric and it is insoluble in water. Now, the formation of aluminium oxide occurs generally when you expose aluminium to oxygen. And if you have aluminium and you expose it to air, you have the formation of the oxide, aluminium oxide. And that is the white dust. If you've ever experienced it, when you have aluminium exposed to air, when you put your hand on it, you see that you have a white dust which covers the aluminium. And that white dust is your aluminium oxide. It is what prevents aluminium from undergoing corrosion. Because aluminium can undergo corrosion, but when you have aluminium exposed to air, it forms the aluminium oxide, which serves as a thin film or a thin covering over your aluminium, and that oxide, the presence of that oxide, prevents aluminium from undergoing corrosion. Then in silicon, silicon also reacts with oxygen to give us the silicon oxide, and that occurs on strong heating. Silicon oxide is acidic in nature and also hydrolyzes in water to give us the silicic acid. It is a covalent oxide. Bonding there is covalent. Phosphorus reacts with oxygen and it gives us two oxides, phosphorus 3 oxide, P4O6, which has a white flame. This is covalent, acidic, and also hydrolyzes in water to give us the phosphoric acid or the phosphorus 3 acid. And in an excess of oxygen, it reacts to give us phosphorus 5 oxide, which was trivially called phosphorus pentoxide. So phosphorus 4 oxide, it gives us phosphorus 3 oxide. So in this case, we see that phosphorus exhibits variable oxidation state. It gives us phosphorus 3. It also gives us phosphorus 5. In the case of chlorine, chlorine reacts with oxygen. Chlorine gives us the sulfur 4 oxide, which is the pale blue flame. And that compound is covalent. It is acidic. It also hydrolyzes in water to give us the acid. It gives us the phosphorus 4 acid. Again, it gives us the sulfur 4 acid. Again, it can also give us sulfur 6 oxide. So sulfur, like phosphorus, can react with oxygen to give us oxides with variable oxidation state. What we have here is sulfur 4 oxide, and it now gives us the trioxosulfur 4 acid, or if it forms the sulfur 6 oxide, SO3, in excess of oxygen, it will give us the tetraoxosulfate 6 acid, H2SO4. Then in chlorine, chlorine reacts with oxygen and it gives us the chlorine oxides. In the case of chlorine, this oxide hydrolyzes in water and that gives us the corresponding acid. Here it will give us the perchloric acid. But I must note that in the case of chlorine, chlorine reacts with water. It will give us the chlorine 1 acid. It will give chlorine 1 oxide. It will give us chlorine 3 oxide. It will give us chlorine 5 oxide, and it will give us chlorine 7 oxide. So in the case of chlorine, chlorine also exhibits variable oxidation state. So in short, what I have said is that when you have the elements from phosphorus to chlorine, all these elements, when they react with oxygen, give us oxides that have variable oxidation states. In the case of phosphorus, it gives us the +3 and the +5 oxidation state. In the case of sulfur, it gives us the +2, +4, and +6 oxidation state. The +2 oxidation state oxide is not stable. In the case of chlorine, it gives us the +1, +3, +5, and +7 oxidation states. Or argon, which is the inert gas, does not react with water. or with water and also with oxygen. So this is just a summary of what we have for the reactions of the elements. It reacts with for the oxides. These are the different oxides that are possible. We have the ionic oxide. Sodium and magnesium oxides are ionic, while silicon to sulfur oxides or chlorine oxides are covalent in bonding. Aluminum oxide is both covalent and has appreciable ionic character. Then we look at the reactions when they react with water. Sodium gives us, the sodium oxide gives us the sodium hydroxide. Magnesium oxide gives us magnesium hydroxide, which means they hydrolyze in water, they react with water. And we have seen, I mentioned earlier, that the sodium oxide is strongly basic, is a strong alkali. The pH of that solution will be between 13 and 14. While for the magnesium oxide, when you dissolve in water, the pH is pH 10. Remember, I mentioned that magnesium oxide has some covalent character, so it is moderately alkaline. Aluminium and silicon do not react with water. So when you add water to the oxide, the pH is still pH 7. But from phosphorus, sulfur, chlorine, all these react with water and give us acidic solutions. We have phosphorus 3 oxide, which is strongly acidic. We have the phosphorus sulfur 2 oxide, which gives a weakly acidic solution, and sulfur 6 oxide, which gives a strongly acidic solution. And that we see is revealed in the pH of the solution that is obtained. Now we look at the reaction with chlorine. Now, sodium reacts with chlorine to give us sodium chloride. Bonding in sodium chloride is also ionic. And sodium chloride, when that reaction occurs, it gives us a bright white orange flame. Again, is a sodium salt. So it gives us this almost the same color as we have when we have the reaction with oxygen. So we have magnesium oxide, magnesium also reacts to give us magnesium chloride, which also bonds with so it gives us magnesium chloride, which also gives us an intense flame. Aluminium reacts with chlorine to give the aluminium chloride. Sulfur reacts to give us sulfur 4 chloride. Phosphorus reacts again. It can either give us phosphorus 3 chloride or give us phosphorus 5 chloride, because again, phosphorus will exhibit variable oxidation state. Sulfur also reacts with chlorine, and it will give us sulfur chloride. It will give us sulfur chloride. Again, sulfur can also give us variable oxidation states. Argon does not react with chlorine. Chlorine, of course, when it reacts with chlorine, it gives us the chlorine molecule. So that is not any reaction that we are interested in. So the reactions with chlorine. And if you look at the trend with the reactions with oxygen, reaction with water, reaction with chlorine, you see that when you have sodium is always ionic. When you have magnesium is ionic, but can have the covalent character because of the high charge of the magnesium and the strong polarizing power of the magnesium ion. Aluminium gives us ionic or ionic covalent, and that compound is usually, whatever aluminum compound gives us, is usually amphoteric. Phosphorus, sulfur, chlorine, as the case may be, gives us covalent compounds. And we have the diagonal. In the periodic table, we have what we call the diagonal relationship. The diagonal relationship was observed between elements of 2 periods, that is 2 succeeding periods. And it's observed mainly between elements of period 2 and the elements of period 3. And it is the situation in which elements in the second period or elements in period 2 exhibit a close chemical similarity with elements, their diagonal neighbors in the next period. For instance, we have lithium, which is period 2, group 1, exhibiting a diagonal relationship with magnesium, period 3, group 2. So we see that this arrow tells us lithium is related to magnesium, beryllium is related to aluminium, so it is the element to its right. Boron is related to silicon. So we have that relationship is said to be a diagonal relationship. Now, the basis of the diagonal relationship, different books explain it in different ways. But the basis is basically the similarity in the charge to size ratio of the elements. So the size to charge ratio of the elements are similar. And as a result of that, the elements as cations will have a similar polarizing power. For instance, lithium is a group 1 element. It will give us a charge of +1, and the size of lithium, so the division of the ratio of the size charge of lithium to the size of lithium is about the same as the ratio of the charge to the size of magnesium. And so because of that, they will have a similar polarizing pair, and that will give the compounds that are formed similar properties. So the polarizing pair in the lithium plus ion and that in the magnesium 2 plus ion is similar. As a result of that, the chemical properties of the compounds that are formed will also be similar. So that is the diagonal relationship. Now, this relationship I've mentioned is similar basically due to the charge, okay, says the size to charge ratio, and that is reflected in the polarizing pair and also reflected in the electronegativity. So the diagonal relationship is quite important. Lithium and magnesium, beryllium and aluminium, boron and silicon. So in the case of some copper similarities in properties between lithium and magnesium, both of them will form insoluble carbonates. So the carbonates of lithium and magnesium are both insoluble and they decompose on heating. Whereas for the other group 1 elements, the carbonates of these elements are soluble in water and they are stable. They do not decompose on heating. But because of the similarity in the size to charge ratio of magnesium and lithium, they have the carbonates behaving in a similar manner. Also, the diagonal relationship is reflected in the chemistry of the chlorides. Both lithium and magnesium form hydrated chlorides. That is, their chlorides are surrounded by water molecules. While magnesium gives us the hexachloride, lithium gives us the dichloride. All other group 1 elements do not form hydrated chlorides. Now, the hydration is because of the high polarizing power of the lithium ion. So all others do not give us hydrated ions. Also, for the oxides, both lithium and magnesium give only the simple oxides, while the other elements of group 1, in addition to the simple oxides, give us the peroxides and the superoxides, as the case may be. So when lithium or magnesium react with oxygen, you can only have the simple oxides. Simple oxides are the oxides in which oxygen it has an oxidation state of -2. But the peroxide, we have the oxidation state of -1, and the superoxide, the metal element, has the oxidation state of -0.5. That is, oxygen in that has the oxidation state of -0.5. Also, lithium and magnesium ions are heavily hydrated, and that again is due to the similarity in size to charge ratio. Because of their charge, and the size, that ratio is about the same. So those of them are hydrated. Also, most group 1 elements do not give us hydrated ions. So that is the similarity between lithium and magnesium. Again, both of these, for beryllium and similarity between beryllium and aluminium are both passive metals. They do not dissolve in nitric acid. They also dissolve giving off hydrogen. Both of them dissolve giving off hydrogen. Both beryllium and aluminium give amphoteric oxides or amphoteric compounds. That is, both of them are amphoteric. The metals react with both acid and alkali. Both of them give us the amphoteric oxides. The oxides also react both with acid and alkali to give us salts. Then also, both beryllium and aluminium give us electron deficient chlorides. Electron deficient chlorides. That is, in both aluminium chloride and beryllium chloride, the octet rule is not satisfied. And that means that these elements, these compounds, both the beryllium and the aluminium compounds, their halides, can exist as Lewis acids. They are electron deficient, so they can exist as Lewis acids. That is, they can readily accept electron pairs to form a stable compound. So that is that about beryllium and aluminium. Now, in the case of boron and silicon, both of them give a wide variety of unstable hydrides. We have the group of hydrides we call the boranes, that is the boron hydrides, and also the group of hydrides we call the silanes, the silicon hydrides. So both of them form hydrides, and the hydride is not only one, they form a series, a variety of hydrides, and these hydrides are unstable. Both boron and silicon are weakly acidic. When they react with water, the boron oxide with water, silicon oxide with water, they give us the acid, boronic acid, and silicic acid, which are both weak acids. So the oxides are weakly acidic, react with water to give us a weak acid. The chlorides for both boron and silicon are volatile chlorides, and they undergo hydrolysis to give an acidic solution. So they undergo hydrolysis, they are hydrolyzed to give us an acidic solution. So with that, we conclude the periodicity of the period 3 elements. So we've looked at the period 1, the periodicity of the physical properties. We've also looked at the periodicity of the chemical properties using the elements in group period 3. And I mentioned why we use the elements in period 3. And we also looked at the elements. We have it starts with the metal, we end with the non-metals. Another thing you might have observed here is that for the non-metals, we have the compounds have the possibility of having variable oxidation states, or the atoms can exhibit variable oxidation states. And that starts mainly from the phosphorus. It is pronounced from the phosphorus family to the chlorine family. Carbon can also exhibit variable oxidation states, but the oxidation states are limited because of the D block elements. So that is that about the periodicity of the chemical properties. So on Wednesday, you will start with the group 1 elements. So thank you very much. I enjoyed having your class, introducing the inorganic chemistry aspect to you. So from there, we now go to your group. So Wednesday class is okay. So we end the class now, and on Wednesday we start with the group 1 elements. Dr. AGR will start with you on Wednesday. So enjoy the rest of the course. Bye-bye.